In Østerbro in Copenhagen, there is an old apartment building from 1925. In April 1994, inspired by the ideals of urban ecology, a low-energy renovation was initiated, which was completed in January 1995. The apartment building contains 72 apartments. There is also a kindergarten, a dentist, and 5 shops on the ground floor, facing Østerbro. The builder is the Danish Housing Association, AAB. The architect is Claus Boyer Rasmussen from Bygningskontoret. This firm of architects has also been responsible for the supervision of works. The comprehensive approach to energy saving has been worked out on the basis of an idea of Peter Weissig Petersens from Lavenergirenovering Energy Consultants, who are also consulting engineers on the low energy design. The project has been carried out with financial support from the EU Thermi programme. It has been the aim of the project to save 50 to 60% of the district heating consumption. To achieve this goal, several important steps had to be taken. It is these we are going to look at now. The old windows were in a very poor state of repair. They didn't shut properly and had only one layer of glass. This meant both drafts and a considerable loss of energy. One of the most cost-effective ways of saving energy often involves replacing old windows with new ones. But at the same time, one has to be aware of the fact that the building's appearance might change considerably in the process. The windows that had to be replaced were of the type known as the Danish national flag window, part of the Danish architectural tradition. There was an express wish to retain the old style and at the same time obtain the greatest possible reduction in heat loss. Cooperation between Lavenergirenovering, Bygningskontoret and Rationale Windows resulted in the development of a new type of window. It has 3 layers of glass, 2 of which have a low emission coating. This new window has been tested at the Danish Technological Institute, where they have measured a total U value of 1.24, based on a so-called hotbox test. This value can be compared to other Danish national flag windows with ordinary sealed glazing units, which have a U value of 2.8. The heat loss is, in this way, reduced by more than 50%. The development of a low-energy window, which looks like the Danish national flag window, has rather wide perspectives with regard to future retrofit projects on newly built houses in Denmark. In addition to the energy savings, the windows will be more user-friendly as they will still open outwards. As the hinges are laterally controlled, the windows can be cleaned from the inside when they're open. Furthermore, the windows are made with a combined wood and aluminium frame, where the outside part is of aluminium that needs very little maintenance. The inside part is made of wood, thus retaining much of the original look. The energy savings seen in relationship to the price of these windows gives an estimated payback time of 8 to 9 years. But if the saved maintenance costs are included in the calculation, an even better result can be obtained. The outer walls facing the yard have been insulated with 200 millimeters of external rock wool insulation, with a subsequent brick facing of the ground floor and a final plaster coat applied directly on the insulation layer on the upper 4 floors. On the basis of consultations with the city architect regarding the building's architecture, the external insulation is limited to the walls facing the yard. Additional insulation has also been carried out in the loft and below the windows. Red, sand-faced bricks that harmonize with the facade cover the ground floor wall. The upper plastered levels are in light yellow and act as pleasant light-reflecting surfaces. The only change made to the facade has been the installation of new windows, and on the walls not facing Østerbro, sun-space towers. The sun-space towers are made in a simple style and are as transparent as possible to supplement the classic simplicity of the building. In order to secure maximum comfort, the glazed balconies can be almost completely opened. On the ground floor, some bays have been placed as single verandas towards the yard. Balconies and verandas are not really great energy savers, but they do provide the apartments with a private outside sitting room, which is of great importance to many people. For the first time in Denmark, a solar wall with transparent insulation has been constructed. The modules are of Capilux TDW. The unit is kept together by an aluminium frame with 6 millimeters of hardened glass on both sides. In the cavity there is approximately 8 millimeters of air and 40 millimeters of capipane. Capipane consists of thin plastic straws which provide excellent insulation and at the same time allow the solar rays to slip through. These modules have been supplied by the Topguard company, while the aluminium frames were supplied and mounted by the GGF company. First, the original wall was painted with black facade paint to absorb as much heat as possible. Afterwards, the aluminium frames were mounted. These secure the fastening of the finished modules and at the same time leave an air-filled gap. This gap has an insulating effect, and here there is space for the preheated air, and some ventilation ducts can also be concealed here. The solar wall works in a number of ways. The 60 millimeter transparent insulation modules act as ordinary extra insulation of the outer wall, but as they're also partly transparent, they also act in the same way as glass in a greenhouse. The black painted rear wall absorbs and stores the heat, which is given off when temperatures fall. At the same time, advantage has been taken of the cavity air, which is used as preheated ventilation air for the apartments behind the solar wall. Fresh air comes into the solar wall from below and is heated as it rises. It can then be taken straight into the apartments from the solar wall. When the temperature of the incoming air gets too high, an air vent opens, so that fresh air is also taken in through a grating above the window. When the temperature gets too high, the solar wall will be automatically shut off. The air vent is controlled by an energy management system, which has a temperature sensor in the air supply duct. At the top of the solar wall there is also an air vent which can be opened and closed manually if the tenants feel that summertime temperatures in the apartments are too high. The air change is controlled in all apartments. This means that there are air extraction systems in the kitchen and bathroom and fresh air ventilation in the living rooms. The ventilation systems have been installed by AAB ventilation. So as not to lose too much energy when the warm inside air is replaced by cold outside air, there are heat recovery units on all systems. The units, which have been supplied by the Thermovex company, are counterflow heat exchangers with a particularly high efficiency level of up to 80%. The hot air that is extracted from the kitchen and bathroom cross the cold, fresh outside air inside the units. In this way, the air is preheated before it is blown into the rooms. In all the apartments, the heat recovery unit and ducts are concealed under a false ceiling in the hall, and the extraction ventilators are located in the loft. In this way, a partial vacuum is maintained in the extraction ducts, and any unpleasant smells are avoided. Placing the extraction ventilators in the loft also keeps noise levels in the apartments down to a minimum. Electricity consumption for the ventilation systems is approximately 100 watts per apartment. If it had been possible to make a common ventilation system for several apartments, further considerable reductions could have been made. 234 square meters of solar collectors to produce domestic hot water are located on the roof. The solar collectors are roof integrated, which means that the solar collector is flush with the roof covering. A large section faces south and two smaller sections face east and west. The three sections can be controlled individually, so that use can be made of the section supplying the heat. The energy management system ensures automatic control. In the summertime, this means that hot water is on supply from early morning until late in the afternoon. To ensure maximum harmony between the solar collector and the roof surface, the ventilation covers had to look as inconspicuous as possible, so special ones were made. The zinc flashing that was laid from the solar collector down to the guttering also matches the solar collector. In this way, the architect has tried to create an affinity between the solar wall and the solar collector. Holes were cut in the flashing and the covers fitted. To reduce water consumption, the old fittings in the bathroom and kitchen have been replaced with water-saving fittings. In this way, consumption will be reduced by up to 25%. The old radiator system has been replaced by a new low-temperature radiator system that receives heat from the district heating network. The temperature is controlled by an energy management system, which is dependent on the outside temperature. When low-temperature heating becomes more widespread, the efficiency of the CHP-based district heating system in Copenhagen will increase at the same time. As the windows are now low-energy, draft-free windows, it has also been possible to place the radiators centrally in the apartments. This has saved piping and reduced the heat loss from the distribution network. The central boiler room is situated in the cellar. With so much technology in one housing block, a caretaker would have a difficult job to ensure that everything was working properly. This has been solved by installing a computer-based energy management system, which was supplied by Danfoss System Automatique. Temperature sensors send signals to the EMS system, which has been programmed to control air vents and pumps and to set off alarms if something goes wrong. Via a modem, the necessary data can be seen on a computer at AAB's head office and at Lavenergire's office. EMS control is almost indispensable when controlling, monitoring and following up new technology and a variety of technical solutions, such as the ones seen in this building project. Lavenergire also uses the EMS to collect data on performance and energy consumption. As the project is supported by the EU Thermi program, the different installations will be measured and evaluated for at least 1 year, so that the way the different solutions function in practice can be documented. The aims of the project are first and foremost a substantial reduction of energy consumption, a better indoor climate, lower maintenance costs, economic viability, an aesthetically pleasing building, and last but not least, that the tenants will feel happier about living in the finished building. The intention was also to show an example of how the government's aim and the aim in the Brundtland report of reducing energy consumption by 50% can be achieved in practice. That is to say, by an optimum combination of the best low-energy and solar energy designs in an old apartment building. Something that has wide perspectives in connection with the future demand for urban ecology retrofit. For example, in urban renewal projects, where, as far as Copenhagen is concerned, very large investments will be made in the coming years.